So we were discussing the problem with Kepler's model of the solar system. So the problem was, we all know the planets go around the sun in an ellipse, and the location of the sun is called the perihelion of the ellipse. Now, when the Mercury goes around one cycle, and then when it goes around the next cycle, the location of the sun or the perihelion has changed a little bit. So that was a problem,
Because the equation is then wrong.
Right.
It doesn't account for this change.
Right. The Kepler's equations does not account for this change.
The Newton one, either.
Yeah, the Kepler's equations are built on top of Newton's equation. So when you look at the Kepler's equations, they were fine. There's nothing wrong with that. So the problem has to be with the Newton's equation. So Newton's equation, this equation has to be wrong somewhere. This force has to be wrong, something. So people start looking into this problem, and it was Einstein who solved it for the first time. And how he solved it is the theory of general relativity. Or he came up with new set of equations called Einstein's field equations, but which we are going to go learn later on. But before that, there was another problem that we have to talk about.
Yeah.
So here we have two cars here, right? One car is going at 100 miles per hour, and the other car is going at 80 miles per hour. Now, the 80 miles per hour person, the driver in this car, the 80 miles per hour car, would see this car moving at 20 miles per hour. And this person is an observer, not moving. And she would see this car moving at 100 miles per hour and this car moving at 80 miles per hour.
Mm-hmm.
So this is common sense. So there was nothing wrong with this picture, but there was a problem happened. Now, what happens when you send a light beam between these two cars? So let's say the speed of light is c. Let's say it's a big number. It's 186,000 miles per second. So instead of writing that, let's call it c. Mm-hmm. So this person going at 80 miles per hour, light is going at c. So he should see the speed of light c minus 80, right? If he were able to measure the speed of, now she would see the speed of light as c, right? Because she's not moving.
Right.
But he's moving, right? This driver is moving.
Mm-hmm.
So he or she should see the speed of light
c minus whatever he is.
Yeah, c minus 80. This car is c minus 100.
Mm.
Right? But that's not what was happening when they did the experiment, not using cars, but various prisms and all that. Everybody, the lady would see the light moving at c. This driver would see the light moving at c. This driver also would see the light moving at c. The speed of light is constant. Even if you move.
Is it because it's so big that it goes through a threshold?
It's big, but when they did the experiments, they accounted for those. So these two people, Michaels and Morley. So that question came up when they did the experiments. Because the speed of light is so big, whatever they did, but they made it very, that question was answered. They made the experiment, which we are not going to go in here. It's a very complicated experiment. And everybody agreed the experiment was correct. And others also came up with different types of experiments. And everybody, even now, 2200, today's 2023, and still everybody has measured the speed of light is a constant. The question that because the speed of light is very big, and then the whatever they are measuring is small. The difference is very, very small that they could not measure, and that was answered. They made much better and better experiments, and still that the speed of light came to be constant. So that was another problem that came about. So we have two problems now.
So is only the speed of light that is constant, or is there any very fast speed?
No, only the speed of light is a constant. Speed of light, and then the gravitational waves. Anything that does not have a mass. Anything that does not have a mass would go at the speed of light. Neutrinos, light, gravitational waves. And if something that has a mass, electron, and if you accelerate to the speed of light, then it becomes massless. Mass would convert to energy, and it would be massless. So it's the gravitational waves goes at the same speed as speed of light, and neutrinos, they're going at the same speed as speed of light. So now here you have speed of light as c, and then there's a rocket that is going at c by 2, just to elaborate the point. And now he would also measure it to be c. It's not going to be c by 2, right? Because he's moving so fast, but the speed light would go past him at the speed of light c. It's a constant. Doesn't matter how fast we move.
Yeah, no, I got that.
So this was a very big problem now. This has to be resolved too. So we had two problems.
It's because the equation has times m or something, which is the mass, and then that masslessness makes a difference.
Right. When the mass changes when you move. So these things were never kind of like just because someone is moving, why would the mass change? Not only mass, the time changes too.